Mr. Ryan, how are you today?
Good.
Okay, so this is the binary tree, and the green ones are the biggest. Then all its descendants, right? It could be bigger or equal than the maximum value of all these subtrees, right? For example, 6 is maximum. What's the biggest in this subtree?
6.
6 is bigger or equal. 3, the leaves are okay, right? Leaves, of course, for the leaf nodes with no children, obviously they are the biggest of their descendant because they are just themselves, okay? And then 2 is not, right? Because the biggest is 6, it's not. Alright? So we want to count how many nodes satisfy leaves. How many nodes? Okay, so each node.
4.
Yeah. How many? 1, 2, 3, 4. So because
And
these.
there's a big brain.
Yeah, these 4 nodes,
Please,
Ryan,
small
please
bits.
keep quiet. These 4 nodes are the bigger or equal than the maximum of its descendant trees. Alright? Yeah? So what's your idea?
Brute forcing.
Yeah, brute forcing might work, okay? Brute forcing. So how do we brute force? We brute force for each node. For each node, we can brute force each node. For each node, we just check. We just go through the subtree again to find out the maximum value, right? But let's going to take what's the time complexity if you go n square, yeah, we're done. Because if there are n nodes, right? And then you visit for each node, you need to visit the subtree, and that's going to take roughly O n, right? On average, O n2, but the time complexity is O n times n divided by 2, which is O n square. Okay, that's 2 stuff. How about if I tell you that at some point we know the maximum of left tree and then the maximum of right tree, right? I know obviously at this point we know what? We know the maximum of left tree and maximum of right tree. We can do this recursively, right? And then we know the current value. And if the current value is bigger than the left max and the right max, then we increment the answer. Make sense?
And then you return the answer.
No, for this one, then we return, for each recursion, we do this, we return the maximum of the subtree, okay? If, look, this tree, okay, I have a note. What's the pre-order for this tiny binary tree? What's the pre-order? Ryan? Pre-order.
No.
Yeah, one,
1,
2.
2, 3.
What's the post order?
2. 1.
Post order.
Oh, 2, 1. 2, 3, 1.
What's the in order? Ryan, what's the in order? If you want to visit the one in the middle, what's the in order?
1, 2, 3.
No, let's pre-order here. What's the in order? Come on, can you stop drawing?
In order is
We want to visit,
2,
yeah,
1, 3.
2, 1, 3, okay. So now, look, if we visit a tree with the post order, recursive post order, we visit the left tree first, we visit the right tree first. For each recursion call, we return the maximum of that subtree, right? Alright? At this point, we know the maximum of the left tree and the maximum of the right tree. And if this node, the root node, is bigger than the both, then we increment the answer. Right? Make sense? What did Steady say? You're busy drawing.
Increment.
What increment? What the
The
increment?
answer
What increment? How are we going to implement this?
by incrementing the answer.
Are you finished or not?
No.
Okay, I wait if you finish. Wow, what you drawing?
Ryan, I'm drawing a doodle, right?
Okay, come on, that's it. No more, come on, can I have it?
It starts with shooting stars.
Okay, so now let's say count maximum, okay, count maximum, okay, count maximum. And then we have the root, what's missing?
Color!
Okay, and then now we want to accumulate the answer here, answer equals 0, and we have a post order, yeah? Depth first search, post order, root, So what's this function return, by the way? What's this function return?
It returns the depth of search L.
What are we talking about? Look, I just said for the post order, yeah, post order. If I'm at this point root, so this is the left max, the max of the left tree, the right. So what should I return for this depth of search? The what?
The
Left.
left and left.
What should I return?
Max.
Yeah, and then what's at this point? I need to return what?
You need to return if root is greater than left max and right max.
For each recursion, we just want to return the maximum value of that subtree, right?
Yeah.
And then it can be compared by three values. What are the three values we need to compare?
Root, left max, and right max.
Yeah, root of value, left max, and we can do this recursively in the bottom up, right? In the bottom up. So we pass. So we pass top. Yeah, we pass along the way. Okay. So look now, if the root is empty, what should we return? The maximum.
Nothing. One.
The very small value. What can you think of? The smallest value you can think of.
Infinity plus one.
Why you plus one? Max dot infinity, yeah?
Mass dot infinity and one.
No, we don't need the one, okay?
Why?
Why you need to plus one? Yeah.
No. Return math dot infinity then one.
One? What the one is coming on?
Infinity and one because infinity and one is smaller than infinity.
Well, okay, so you mean no. Max infinity is the smallest number we can think of. Okay,
Yeah,
now
but
look.
I can think of something better.
The post order, we just say the post order. Post order what? Post order, this is the root. And then this is left. This is right. So what's the post order?
Post order is left,
Left?
right, and root.
Okay, so left equal DFS root of what?
Root dot left.
And then
Root dot
right
left.
equal what?
Deficit root dot right. Minus infinity. Just kidding.
Root of right. Okay, so now
Why do you have a minus infinity there?
okay. Okay, so I have left, right. So now return what? Return what? You just said return what? Max of three values.
Max of left.
What?
Max of right.
Wow. Root of what? Root of value. And then what? What two values added? Two values.
And root dot line.
No.
Left dot value and root dot right.
So no, come on. Root of value and left and what? Left is here.
And right.
Right. So
I
because
didn't
this
say
one.
that.
Okay, now at this point I need to compare. I need to increment. At what cases I need to increment this answer? Okay, I need to put it here. There's a non-local here to allow us to increment this value. Yeah, non-local answer. Okay, so in what cases we need to increment the answer? If what? If root of value is bigger than what? Equal than what? Come on.
Bigger equal than left and right.
Yeah, left. And root of value is bigger or equal than right? Because now at this point, this node is bigger. This node's value is bigger than the left tree and the right tree, right? Am I right, Eric?
Yeah.
And answer plus equals 1, okay? And then I just have the DFS root. And then what? Return what? Return what?
Return answer.
Answer. Easy. What's the time complexity? We're visiting the tree. Yeah, post order. Each node is visited exactly 1. What's the space complexity?
No.
Because we're using the recursion post order, the stack, okay? The stack is implicitly used, okay, by recursion, using the stack. The compiler, the computer builds the stack, okay? Yeah? Builds the stack for us. Can you not draw that? I'm gonna ask you questions. Can you explain to me what's this function return? Depth of search.
Answer.
No. Depth of search. What's this function return?
It returns return max, root dot value,
What
left
is-
and right.
Yeah. Then what does
It
it?
means that you return the maximum of this and maximum this and
No. So what's
and you
this?
compare it with this.
Okay,
and
then
this
return
and
the what?
this.
Return the maximum of the value in the current subtree, right?
I literally said that.
Yeah, you need to express it well, okay? I know you understand, but you need to try to express it, or you try to explain to people, okay? Make sense? Ryan, do you understand? Any questions so far?
No.
Okay, that's it for today. Bye bye.
Bye.
Bye bye.
Bye.